Okay, so we can start the second lecture of Eveliina Peltola about probabilistic tools for conformal theory.
Yeah, thanks. I'm completely confused about the time, so please just stop me when it's time. So now we actually already learned what these random curves are that I'm talking about, but maybe let me recap because I want to go to the interaction of them. The easiest recap is the picture, right? So the motivation was coming from some lattice model, like easy model, or some square grid or whatever. And then you can put these colors that we already saw in Johan's talk in other models, like plus or minus spins or whatever.
But they are not really completely defined yet, no?
The colors.
No,
Silly. Yeah, I will define it. But I hope you remember last time how I was motivating it, right? Is that if we have some kind of critical model, let's say, which has these spins, right? Sigma, which is plus or minus 1. In the interior, somehow randomly, according to this Gibbs measure. And if you have boundary conditions, so with boundary conditions, which somehow alternate, so some segments on the boundary are plus and some are minus, and you could have more than 2, but here I just draw 2, right? And inside I have the statistical physics model that has random configurations whose limit should be a conformal field theory, right? So now the boundary conditions I encode in some disorder insertions. So maybe here is some point x and y. And of course, if x is telling me that on the right side of x there's minuses, left side of x there's pluses, y is somehow the opposite, because we are in 2D. Remember? So we will see a domain wall between the pluses and minuses from x to y that I think we saw already in Johan's talk, not in this model, but other models, right? So I could follow the pluses and minuses wherever is the disagreement. And I find this curve. And of course, there are also loops, which I will not talk about here, but we heard about them quite a lot. And all of them should have to do with CFT. You could ask about correlations for them, etc. But the simplest one is just look at this yellow guy. So you get an interface, which is some kind of curve. Maybe I can call it eta. It goes from x to y in this domain, whatever I had. And because we have a conformal invariance that we expect, I think I ended last time saying that actually I could just go to my favorite domain by conformal map. And for the moment, my favorite domain is the half plane. And I'm going to be having x goes to 0 for simplicity. Okay, y goes to infinity, which is the boundary point in the half plane, right? It's a subset of the Riemann sphere. And then I have these pluses and minuses emerging there. But of course, you know, if I have a discrete thing, I need to worry about what happens in this kind of unbounded domain. But let's forget about the discrete, because we actually want to study the continuum model. So maybe I can say here something that I already mentioned, which was proven by Smirnov, maybe et al, because there was some technicalities. I'm not sure I can put any year there because it was in, someone remembers better than me. 2010 around maybe was more or less complete. Already before there was the idea. Is that if I take this easing interface, maybe I should here have some little delta. So this is some delta times delta grid originally, right? And the scaling limit means delta goes to 0, so the grid disappears. So the result says, kind of roughly speaking, that we know what the limit object is. So I write here SLE3, which is the SLE that I need to define. And there can be other variants of it. And so if you're a mathematician, you ask, what does the convergence mean, which topology, etc. So this is a random curve, right? Random object. So it has some measure, probability measure.
What is the parameter that you put for the SLE?
Let's maybe put kappa here. And kappa happens to equal 3. So I'm gonna tell you what the kappa has to do with central charge very soon. Okay, so it's some parameter, and I need to tell you what this guy is. So this is a mystery for if you pretend you didn't see any talks yet. But just to say what the idea is to forget about the lattice is that I have some random curve in the discrete on lattice, right? But it goes somehow on the, so I could have made a bit zigzag looking curve. It's still a continuous curve, it just makes turns in the lattice. And in the limit, it becomes something which is not smooth, it's very, very fractal, but it's still a curve. So here should be also a random curve. But now it's in the continuum domain, which maybe in the left-hand side was this D. And because we have conform invariance, which is a property of this, so it's not part of the theorem really. Let's do like that. Implies that I can just say, yeah, let's consider D is the half plane, and okay, then I need to understand what is this side. But if I understand this object in the half plane, then I understand it in these other domains. That's the point. And the convergence here, yeah, so there's various ways to formulate it, but it's a weak convergence of measures. Of probability measures. So if you don't know what it means, don't worry. It was just because some people wanted precise statements, so they said a little bit more precise, right? But we don't need it later. So because we have a random curve, we understand it as a probability measure of all possible curves from X to Y. And I want to say that those probability measures converge to some probability measure here. And the topology is unparameterized curves, but yeah, maybe I will not write it. So point of the theorem being that the motivation makes sense. So you can actually prove that these discrete guys in certain models including the Ising model, they converge to this SLE object that is somehow the key topic of these lectures, maybe. Hope it motivation kind of helps. So then what I need to do is to tell you what is this, right? Right? And I could say it's a conform invariant random curve. But so what does it mean concretely? So I can generate it in the half plane somehow dynamically. I think that's the most intuitive way to think about it. Because from here, if you imagine how the yellow guy was obtained, is that you start from the boundary where I have this boundary condition changing operator, then I start following where these pluses and minuses go. I explore, so there's some kind of direction naturally here secretly. Of course, it doesn't matter if I go from y to x instead, but I can pick a direction. And then here I can also imagine I'm following some whatever was causing this guy to be here. So that's why I want to call it evolution. And Schramm and Löwner, maybe I already mentioned. Schramm was introducing this object for this kind of perspective in mind. And he proved some other convergence results. Löwner is a complex analyst long ago who had a theory for this kind of evolving domains. So combining these two, so with randomness, you get this object. So maybe a little bit more concretely then. So I just say it's a random curve in some domain, those points. And because by conforming variance, we take half plane, 0 and infinity. And I can construct it as follows. So let me draw the picture again. Let's call the curve, I think it was eta. So eta, I have some kind of parametrization from the evolution. So it takes time variables and goes to the plane, right? At time 0, it starts from here, which was x. And actually what's going to happen is that when time goes to infinity, in my chosen parametrization, it's going to go to infinity. So I can imagine it to be curve from 0 to infinity. And if I map this back to the bounded domain, infinity becomes some other point, which is a bit nicer to imagine. So that's why usually I want to draw in this way. But the formulas are horrible, so it's easier to draw formula in this geometry. Okay. So how do I construct it? Is that for each time, so let's imagine it's just a simple slit like that. So I want to find out where is the eta t at time t. And I know conform invariance. So what I can do is I can map the outside. So half plane minus this initial segment back to the half plane, because it's my favorite domain. I always uniformize. The key is to uniformize because we have conform invariance. And then, okay, so now the pluses and minuses are gone, so I'm allowed to use red again. Okay, so here is some image of it, the tip that usually we call WT, subscript for kind of stochastic process we usually use in this way. And how to say? So if I know for all times where the tip is mapped, I can go backward because this is a conformal bijection, this tip. Right? And then I find where the curve was. So if I tell you a recipe to construct it, that's kind of a definition. So I don't want to do an axiomatic definition because I think it's more intuitive to see what it's doing. So what I claim here is that if I plug here Brownian motion that we heard about, but in one dimension, and this parameter kappa, I will construct the correct object. So this is somehow speed parameter. So it's some non-negative thing. It's the variance of this process. And this is a one-dimensional Brownian motion. So it's the unique one-dimensional process which has stationary independent increments and a certain scaling property. But the point is that it's somehow universal, and it's the only possible thing you can put here so that you get a conformally invariant measure, which has some kind of Markovian property that was mentioned earlier. So there's not much choice to put here if you really want to describe this kind of critical interfaces. So that was a long endeavor to understand what it is. But you can define it in this way. So plug in Brownian motion into this picture. Solve this equation for the G, which I didn't write yet. So GT, solve certain evolution equation in time. So I can take the time derivative, and then I'm studying some point, right? So it sends points somewhere in points in space, which are not on the curve yet, goes to some point. And I can ask, how does that time evolution of the point, how is the time evolution if I differentiate in time? And there's actually a formula which is from Lerner theory. Which looks like that. It's a bit unintuitive maybe when you see it the first time. But here appears this, this W. So somehow what this guy cares about, the time evolution, is how close this point is to the curve. Because if it's very close, you think about what is the conformal map doing? It's kind of unzipping this yellow zipper. So then the flow goes like that. So very close to the curve, there's a lot of flow, right? So then 2 over the distance is big, right? And if you're far away from the curve, somehow it doesn't matter too much. Okay, so that's the idea. And there's initial condition, of course, at time 0, nothing happened. So this is an initial value problem in time. It has some lifetime. So if the distance goes to 0, which means that the point somehow, the curve might hit it, for example, then you blow up and the solution doesn't exist anymore. So maybe in this picture, I should have drawn the flow, and then the curve is kind of collapsed there, and the future would go like that. And there was a normalization choice here. So if you remember the uniformization of simply connected domain, there is the PSL2 amount of different degrees of freedom, right? So you need to pick some normalization. But I think for my purposes, it's not so important. It's written in the notes. But there's a consistent way to do it. You see this equation, this number 2 is kind of from the normalization, okay? And so the upshot that could be formulated as theorem of Schramm is that the only possible random curve on this side that has a chance to describe scaling limit of a conformally invariant scaling limit of some kind of model with this Markov property has to be this thing. Yeah.
So GT is not defined at 0, right? But
time 0.
No, GT is not defined at 0.
Z.
Yeah.
Yes.
But if you approach from like left and right, is it possible to? Is it a finite value on the boundary, or is it not?
So somehow this bit, if you think what is happening, is going here, and this other side is going there.
So there will be some finite values there.
Yes, so it's not such a bad. It extends to the boundary, but you have to know which side you go, right?
Yeah.
Yeah.
But I'm just wondering, so it will be like you're showing the kind of zipping, and there will be like limiting point from the left and from the right.
Exactly. Yeah. So you can keep track of this, which is like how far this curve already is spread. Indeed.
But we're still evolving. It will be like getting.
Yeah. So they will go further and further, and yeah. Yeah. And I was cheating a little bit because if the speed is too high, this curve is not going to be such a nice one, but it will make some bubbles. And then you need to be more careful. So let me draw. I hope you're kind of satisfied with the sketchy definition. So this speed kappa determines some geometric properties of this data. For example, what happens is that if the kappa is between 0 and 4, 4 was Johan's favorite value, I think. So then it's exactly like that. So it's just a simple curve. Simple means injective. When kappa is between 4 and 8, okay, it makes bubbles. So it's somehow growing and touching it back itself. It can touch the boundary like that. And then those bubbles are swallowed somehow, so you don't see them from infinity. So you have to think about what the map becomes. So somehow have to involve also all those bubbles, right? The map is not defined anymore.
So what you're drawing right now is the inverse of G that you get for different kappa? Is that
right? Yeah. For different kappas. And of course, I need to prove that if I solve this, I actually get the curve, and this is very difficult, but I'm not going to prove it because I hope you believe it from this discrete picture. Actually, not easy at all to prove. Yeah. So I'm trying to tell you a recipe to understand what this object is. And all you should somehow know a little bit is this what Brownian motion is. But you can do a simulation and you see the Brownian motion is the W, right? With some speed kappa. It's just going to do a random process on the real line. And if the kappa is very large, then it's moving a lot, right? And then when you invert this G, you see that the curve is kind of winding a lot. So here is already winding kind of more than in here. If kappa is 0, so the W is 0, you can solve it and it's just a straight line. It's a little bit possibly boring, although I don't think so, if you have more of them. Anyway, okay, so then I could have kappa very big. And then it's space filling. I don't know how to show it anymore. So it's kind of gonna go all everywhere. Yeah. Right.
Next question.
Sure.
Is there something special about integer values? Use them from other?
Yeah, so many integer or rational values correspond to these kind of models. So now for the easing, yeah. And okay, so you can see it from the conformal anomaly that I wanted to tell you about, because we kind of expect the conformal central charge in easing model to be 1/2, right? So then if you do the computation that I didn't do yet, you can see this value from there. You can have others, like which models you like percolation as kappa 6. I guess for easing, you can also have this 16/3, which has this cluster, represents the clusters, but we don't need it.
I'm going to write the transition formula from kappa to C.
Yeah, you can do it already. So C is gonna be, to remember it correctly, always off by minus sign. So let's see. I wrote it somewhere. You can maybe check quicker.
3 and 16/3 will.
I think there's probably minus sign wrong. Right? Did I write it?
Yes, the minus
there's
sign
a
is wrong.
minus sign.
It's minus. Yes, exactly. So, okay, it's maybe not so illustrative, but you can see, maybe I can use the different color. So this is less than 1 when the kappa is between this 0 and 8, right? And kind of bigger than 8, maybe you care too much for now, because I wanted to have some correlation functions of these curves, and if there's space filling, it's a bit, you know. And if kappa goes to 0, right, then the C goes to minus infinity. So this is the semi-classical limit in this context. And here is actually interesting stuff. So if I have time, I will try to tell you something. But you see really different features depending on the speed. And there's some miraculous way to associate which central charge has to do with which kappa. And I wanted to tell you a bit about the miraculous way, because it also motivates how to get this interaction. So now I could have more curves than one, right? But first we need to understand a little bit this one curve. But maybe before that, are you happy, or do you have some more questions?
Yeah, I still have this silly question, because is there anything on you explained integer values as that they are connected to Ising and percolation and what's not. But
yeah.
is there any explanation on geometrical side that these values give some special properties to these curves or anything?
For the curves, I don't think so. But for there's some representation theory. So you can actually construct a Virasoro representation at those disorder insertions. And there's the central charge, and then there's the conformal weight that will appear in this formula, I'll tell you. The conformal weight that corresponds to that insertion field. And for this kind of integer or rational values of kappa, that conformal weight may be in the range where the Virasoro representation theory is not semi-simple. So there's some kind of weird phenomena on the algebraic side. But many of these objects in the analysis side, if you calculate something, it's just going to be continuous in this parameter, so you don't see much. Yeah. So I don't have a very good answer, except that there's some mysterious thing in the algebra of the guys in these values. And it should have some logarithmic features and whatever. So, yeah. Anything else? So I wanted to, let's see how far I get. I didn't want to spend an awful amount of time with the conformal anomaly, but I want to tell you what it is trying to say. So let's have our domain. Now my favorite domain changed because it's easier to draw. So from there, you can go to other domains by sending everything by conformal. So let's say it's like that. And then I want to see if I change the domain, what happens to my curve? So let's say it's the simplest thing is just I remove some blob A, which is in the domain. Maybe the domain is the disk, let's say. And I want to compare, so this SLE kappa in D, I guess it's from X to Y, which are those points. And D minus this A. And okay, so I assume the A doesn't eat up those endpoints because otherwise it doesn't make much sense. So what is the difference of the two?
E minus A must be simply connected also.
Yeah, so I assume a lot of things, so like in the picture. Or well, if it has some components, then the curve is only in one of them. So this is the stupidest, simplest setup, and you can do much more general. I think for the purposes of the formula, it's sufficient, right? So I kind of want to write it in a measure theoretic way. So let me say over here, because what the random curve means is a probability measure, like was here, maybe P. So I can talk about the law or the probability measure of this SLE in the whatever domain I have, right? So what does it mean is that the randomness that comes from the Brownian motion and from this construction, because I need to know how to sample the random curve because it's random. So each realization has some probability, and that's given by a probability measure. So I just want to give a name for it, which is P, I don't know, like dxy. Because then in other domains, I need to push that probability measure. So there's a push forward measure to the other ones. So it's just standard measure theory stuff. But to compare in different domains, I need to compare these measures. And what is comparison of measures for analysts is Radon-Nikodym derivative. So that's why I want to introduce the notation. So if you don't know measure theory, I think you can get the idea anyway. So it's just symbols. So let's see, I'm interested in the B minus A. And I already know it in D, let's say. And I have my curve. Theta.
Sorry for silly question.
Yeah.
Could you say more about the probability measure? What is it really measure on?
So it's a measure on space of curves. Eta, which are in the closure of D, such that maybe eta intersected with the boundary is just this xy. And maybe I want to put some other, you know, the picture is like that. And maybe it could, okay, this is actually not good because it might touch the boundary if the kappa is too big.
Are they all simple?
Not necessarily, yeah. Wanted to hide the, okay, so they can do like that. I guess just curves such that eta, okay. Started at x, ending at y, because I don't want to fix a parametrization. So then there's modulo parametrization, time parametrization. So I chose a time parametrization for the construction because it's easier. But if the time goes faster, I can do the same trajectory, right? So it's not very, so you can actually forget it somehow. This, yeah, it's very complicated to make precise unless I spend a lot of time. And some, yeah, I guess I could call this space something. I even have a notation in the notes, I think. So this is all curves in D closure that go from X to Y. And maybe here continuous curves and modulo any parameterization.
Continuous representation.
Yeah, because you want it to be a continuous curve. Yeah.
So in the example that we're looking at for the above, is this related? I mean, by B sub T, are we picking a probability measure? Or how
Yeah,
does
so
that relate?
exactly.
How do I see
So this probability measure comes from
the
the,
Brownian motion choice?
so it's somehow inherited from, yeah, from the Brownian motion. B. Because there's, okay, nothing random here, it's just a formula. What's random is what I plug in, right? So all the randomness is from the Brownian motion, but then I need to understand it as a random variable in space of curves, not in space of one-dimensional thingies. And that's why I need this conform map. And this is somehow the gist of this Loeffner's theory. This is called Loeffner equation. It's a big topic actually to investigate this. But for us, yeah, there's randomness that comes just from here. And somehow, if you go back to the piece grid model, there was randomness inside in the Gibbs measure. And you can maybe somehow think about the lattice path. So this is a little bit wrong to say, but there's some kind of random walker, right? But the random walker knows whatever is the spin model here. And then if I take this limit, random walker becomes Brownian motion, but it's not quite true. So I need to understand in this way that only those guys somehow described by the random walker, and I need this input from the somehow conform maps. Yeah, it's really puzzling when you see the first time, I think. But yeah, so then if I really want to do kind of rigorous mathematics, I need to say, okay, so it's actually a probability measure not just one curve because it's random. But in practice, I'm just imagining it as like that.
But also I could put something different than boundary motion there.
Sure. So you can put any right continuous left limit object, but you don't always get the curve. You get some other growing blob. And it's quite fun to study them, but very technical. You can take a Levy process. I was doing it recently. Very ugly.
Okay, and for the correspondence with conformal field theory, I want Brownian motion though.
Yeah, because Brownian motion is the only one that gives you the scale invariance. So I didn't write it. But of course, I expect conformal invariance. Scaling is one conform map. And in the half plane, scaling is kind of doing nothing. And the 0 is fixed, right? And infinite is fixed. So I need this eta curve to be scale invariant. And if I do computation from this theory, I get some scaling property for the W, which is exactly what Brownian motion has to. Brownian motion is the only Markovian guy that has this property. So there's some classification you can do that was mentioned by Johan already. So this is singled out by conform invariance and the Markovian property, which I don't need, so I didn't want to go there. Okay. Up to this parameter couple. This is theorem by Schramm. Was there a question? Okay, of course it's not stated as a theorem, but the point is that if you require, so these are properties for eta, you require the scale invariance, moreover conform invariance, and the Markovian property is that if I stop at time t and I start then growing again, the future somehow only cares about the slit and nothing else, something like that. So maybe you heard about Markov processes. If not, it doesn't matter too much. But if you put those two, there's not much choice. It has to be Brownian motion up to the speed. Yeah.
Conformal invariance would be the conformal invariance with respect to conformal transformations of D, which would fix X and Y, and then we'll have to fix the probability measure, right?
So then exactly the probability measure will be pushed forward, but it has to be the same measure. Yeah, like the push forward measure is the same as what you have. So that's the way to state it for this in the measure theoretic terms. Yeah. Yeah, so there's a lot of consistency conditions, but they all come from motivated from this models actually. So yeah, but so you see, so if I compare different domains, of course, the measure is not invariant because the domain changes. And I was about to write to you how it feels the change and it's gonna have the central charge. So let's see, I think I need just indicator function that the eta is actually not going there because otherwise it doesn't stay in the correct domain. So it's just consistency thing. Then I've got, so here is the C kappa. And I'm using some normalization with 2, but can debate about this. And now we get this Brownian loop measure, which is a little bit maybe hard to grasp, but Johan has mentioned it. So let's see. I will need to tell you what it is.
Sorry, what is the bold one?
What's that?
This bold one.
This means the indicator function that the curve doesn't hit this set because the curve is random. And this actually, what is this object? It's a measurable map on the space of curves, and that's why I have the curve there. Yeah. And this is common notation. It's rather Nikodym of measures. So if you compare two measures, you write in this way, like differentiate one with respect to the other, and you need to, so it's essentially the response of this curve. And this was just to say that we don't get any nonsense, so don't worry about it too much. the anomaly property is more interesting. So let's see. So I need something maybe also happens to those curves. So sorry, those points. So I need here derivative of some conformal map. I need to tell you what they are. Some other color here. Just H1. So there's a lot of symbols I didn't tell you. Let me start from the easiest ones. So if I want to understand the disk minus the A, like which is this one. So from the construction, I need to send it back to some favorite domain. And if I want to compare with this, it's gonna go a little bit maybe, but I hope it's still visible. I'm gonna define this map that is just removing the A. So then I get disk. And the A collapses somewhere, right? And then these X and Y, maybe I'll keep fixed, or yes, I can choose. And then the curve will somehow change, of course, if it's there. So let's say it fixes X and Y, but it collapses this A. So this map goes from D minus A to D, like that. And then I have a derivative of that map at the insertion points. So that's how the endpoints of the curves are feeling the change. And this upstairs has the central charge. So, right. And here are conformal weights of the insertion. So these are not conformal fields. This is just a map. I think my notation is unfortunate. It's capital Phi that people use in the literature usually. So this is just the derivatives of the conformal map. So this is a conformal weight somehow. Which happens to be degenerate in the catch table. So it depends on kappa. And maybe again, my minus sign is wrong. I'll write you a bit better formula soon, which is more maybe familiar. But you see that there's effect to both those endpoints, right? And of course, of the underlying domain. And somehow the anomaly factor is this one that I didn't tell you yet what it is, but you see the central charge. And then you see this kind of other guys. So it's a bit of a long story to explain, but you can kind of compute it. So this is not super hard to prove if you know some probability theory. So there's some martingale argument. So I don't want to prove it because I think it doesn't help anything. But you really see from this change, you collect the correct factors, and that's the kind of anomaly.
So TA is also on the left side, right? Left side doesn't have it, but you pull the one measure along TA, right?
Yeah, so that's the idea, right?
Yeah. On the left, you have this.
Yeah, somehow this one, right?
Yeah, you have to.
This one is the pullback, exactly. Yeah. And then you need to somehow calculate what is the thing. And it turns out something like that. There might be some numerical errors in my formulas. Let me erase this one. And you can ask questions if you have, yeah?
It is, we have seen an analog in the Antoine Diego.
Exactly, yeah.
It is the same.
Yes.
It is the same. So it is, this loop is given.
So he was talking about loop.
Of,
Yes. So I could write it exactly in that way.
okay, okay.
Yeah. Which I was thinking I might do, or I might skip, depending on, do you want to see it? I will write in the notes anyway. So you can tell me which one you want to see and which one you want to read from the note. Because there's a lot of formulas I could write, but it takes time. But it's exactly the same anomaly. And it's somehow believed to uniquely characterize those measures. And in addition, I have those X and Y marked points because I have this chord, right? And that's where the interaction comes, because the conformal anomaly is just telling somehow the response of the change of the underlying geometry. You could think about this chopping off the A also as a change of metric in the disk to some other one. And then it becomes more familiar to maybe people doing this kind of Segal type CFT. So I find it intuitive once you understand a little bit that. I think I might not have time to go there, but that's the idea for me.
And for C equals 0, which corresponds to percolation, being percolation not correlated.
Yep, exactly. Yeah, so if you don't like the anomaly, you can assume kappa is 8/3 or 6. And then the anomaly is not there, but those 5 primes might be there. So for 6, nothing is there, right? Percolation just doesn't feel anything else because it's independent guys. But kappa equals 8/3 is the self-avoiding walk, self-avoiding polymer, and they actually do have some interaction. So if you plug in 8/3, modulo the minus sign might be wrong. You know, you see some non-zero 5 prime thing still there. Right. So what did I call it? I think like that. So Johan actually already explained this, I think. But let me explain again. So here is the A, here's the eta. And okay, it depends on this domain. So I could say it's Brownian loop measure. Which is somehow the 2-dimensional. So yeah, if you somehow lost that, don't worry, I'll write the other formula, which is better. Of those loops, maybe loops L, that's that. L intersects eta, and it intersects A. So this is some other measure, which is not the probability measure. It's some infinite measure. This one. And it's measuring somehow some soup of Brownian loops. I'll just draw the picture and maybe that helps. So what are those L's whose measure we are counting? So given the eta and A, I do 2-dimensional Brownian motions inside, start somewhere, and you do some maneuver to make it do a loop. So there might be those guys. This is not counted because it doesn't touch A. So let's imagine it didn't make a loop yet, but it touched both. So that kind of things. And if the eta is close to A, there's lots and lots of those loops, right? If the eta is far away from A, it's not so many. So you see the effect of how the eta feels this A somehow from this heuristic. But yeah, slightly more precise formula, which unfortunately is infinite for the fractal curve, but maybe I can write it anyway. Aanto wrote it already. So it's heuristically known that the measure of all Brownian loops in my domain, the total mass is minus log of the determinant of Laplacian. And I need to say the regularized, so if you don't know what it is, don't worry. Okay, so I put it downstairs because minus log. So this is somehow all possible loops, but I don't want all possible loops. I want the ones which intersect both of these guys. So then I take away the rest. No, I'm not sure how to write it in the nice way, but maybe I can. Let me put some names there in the picture, D1, D2. So there's 3 in this. Okay, all of that inside the log. Why log? Because we have some exponential there. So now I will tell you, maybe green is back. I'm out of colors. Okay, so this one we call D1, this we call D2, and that we call D3. And this was the whole thing. So I just take upstairs Laplacians in each of these components over here, in the middle, and over there. And if you make the computation, you see that it's kind of measuring where the eta is and where the boundary of A is. Because of course, for this kind of Brownian loop thingy to touch A, it's sufficient to touch the boundary, and then it's doing whatever. So this is one formula.
So these are with Dirichlet condition?
Yes. So this is Dirichlet. I guess Laplace Beltrami, whatever. And of course, it depends on metric. So I'm on the flat. So if you want some other metrics, you can do that. And you can also remember, if you know the Polyakov anomaly formula. So this is related to that. So maybe for people who might know, let me say recall. So if I take free boson partition function on this disk, probably with Dirichlet boundary condition, that is the determinant, right? To the power, I think, minus c over 2 if it has this background, how do you call it, charge? It's a little bit wrong because I don't know how to call it exactly. So still with, you could involve some central charge, or maybe you want it to be 1, and then I think it's minus 1/2 power. So this you see in some CFT business, right? That just the free boson partition function has to do with the Timetov Laplacian. So these are kind of partition functions of that sort. And in CFT, in the axiomatic, say, Segal type CFT, any partition function has this kind of conformal anomaly formula that you can relate to the Polyakov formula.
So this thing can also be put as determinant of Dirichlet-Neumann operation.
Yes, so you can also write it in that way. So then you have Dirichlet to Neumann like on this seam and on this one. Yeah, and you can write it in like 100 ways, probably, also learn energy or whatever. So I don't know which one is the best one. So I thought maybe this will help. Yeah, maybe I should say Alvarez anomaly formula. So this I'm not gonna write, but I can put in the note. So it really relates to partition functions in CFT. And if you do this kind of EG1 type stuff, you always want to have a determinant line bundle, right? And here is a section of that line bundle. How to call it? Yeah. So in fact, we have some on the surfaces where things live, but here we are a little bit stupid because we are simply connected domains. So maybe I should have like, and some metric. So this is a trivial space. So if I would want to do more complicated things, then maybe this plays some role. So it was a side remark for those who like that stuff. I don't want to go there too much. Also because I think I will probably go on forever and ever, and I don't know how long I can still go on. But there's various things you can just associate to this anomaly. And yeah, but the upshot was supposed to be that the central charge will appear there. It's in that formula. And that's one way to see which model has which kappa. Yeah, I don't know if it makes any sense. I know that this object is completely insensible if you haven't seen any of these things. So I hope maybe you believe there's something like this. This is conformally invariant, by the way. Completely invariant. So the covariance are all these other factors. So the upshot is that we have a recipe to compare these SLEs in different domains, or more complicated if you want to do some deformation. There's a kind of similar idea. And it involves central charge and those conform weights. Okay, so this is somehow interaction of the SLE with the domain. Let's say maybe some output, which is very heuristic, is that this C kappa term let's say eta with a domain, or maybe I should say metric or surface, whatever. And then I have this H12, which depends on kappa as well. This is some kind of dependence on the endpoints, right? And if I want more curves, I need more endpoints. And this is where this thing becomes relevant. So I did mention boundary condition changing operators last time. And maybe you guys already know Hardy's predictions. So, you know, let's say in easing, yes, we have that. So I could use the notation of the field, although I don't know what it is. Degenerate. So he was doing computations of what happens in critical models, for example, easing, when you do this plus minus change. And he came to the conclusion that here at this point, maybe it's X, there has to be this phi12 operator sitting there. And then there's another one in Y. So this is one way to see it, maybe. Let's see, how much time do I still have?
Like 5 minutes or 10 minutes?
5 minutes, yes, I think.
So are people comfortable with the catch table or not? So raise your hand if you want me to write down the catch table. I'll write it in the notes. Yeah, so this is so in particular, the corresponding Virasoro module. So I haven't given you any Virasoro, but I kind of mentioned how you can see it here. So there's a possibility to reconstruct it.
So H is the weight, but this is the field.
Yes,
The
so
width
I'm
that way.
labeling the fields like phi,
Right.
yeah, phi whatever, and then the H is this. I think this was, maybe he was also used. Yeah, so this is the field who has this weight, H12.
The field should be an observable of the eta, or?
Yeah, so that's the great question. So what is this field, right? So what I can do is to describe its correlation functions, kind of from this SLE. In some case, when kappa is 4, for example, you can identify using some Gaussian free field things. More generally, I think it's should come from this imaginary coupled Liouville or related kind of things. But then maybe it's not a field in the sense of random distributions. So
But how do you define the correlation function?
right. Maybe this is what I can say. Yeah. So the point is that we have non-trivial submodule in the corresponding Virasoro modules because we're in the catch table. And if you read your yellow book or whatever, you know that there are BBC differential equations for the correlation functions in this case. So how do I define things are using PD theory.
Using
PD theory. So I say that I have a complete set of solutions to this kind of equations. Hence, they have to be correlation functions of this one, but I don't know what this one is. So that's why I said I want to do correlation function point
you
of
need
view.
there are many solutions. You need some.
Yeah.
But even for this, you need to set singular vector to 0.
Yes,
How do you
and we
know
don't
that it's
know it
not-
yet.
How do you know that it's not in your theory?
So I can prove that from these curves, what I get from the interaction, there is singular vector, and
Yeah.
there's the BBC equation. And then I can classify solutions to those. But you're right,
So
so
BBC, it's when you
we
set it
don't
to
all-
0. No.
yeah, so we don't always know if the singular vector is in the theory or not, right?
Right, yeah.
And I don't know what theory. I started my lectures saying that I don't know what CFT is. For me, is I look at some observables that I'm interested in. So here I'm interested in these curves and how they interact. Then I can ask what is in that theory. But yeah, indeed, I don't know. So now I know that potentially there is this singular vector. There might be because I have a cut table. But I still need to somehow see if it's there or not. So you're right, what I wrote there was maybe a little bit misleading, that we don't always get these equations. But in our case, we will.
But this is really confusing because
Ah.
you define a probabilistic object. So there should be a probabilistic correlation function, but you said no, actually I cannot do it. I just say it's a solution of BPZ.
So I can define it from here.
Okay, so you have a probabilistic definition of the correlation.
Yes, yes. Let's see if I'm able to write. I think if you allow me that time, I will write you the definition, which I claim satisfies the BBC.
Okay.
So this was to motivate why this catch label is appearing is from somehow here. Or you can do some other argument. So now, very briefly. I want the things correctly. So the point is that for 2-point function is a little bit, I guess I could study the BBC equation for 2-point function, but it is not very good. So let's have a 4-point function. And I'm in this boundary CFT, so the points are there. And I want to have a pair of curves, right? So maybe there's, let me decide that they go in some way, x1 to y1, x2 to y2. Right? And now I need to define probability measure of this pair of curves. So I don't know yet how to do it. I can just do one, right? And this formula here is supposed to tell me how to do it. I don't know if I can impressionistically do that, but forget about the A. Let's say the boundary of A was this other curve, right? So then we know something, right? But I could also think about this bit as A and this as the curve, because there's some symmetry. I can pick which one is my favorite curve I'm considering, and the other one is kind of fixed. So maybe there's eta 1 and eta 2. Is this there? So one a probability measure, let's write in this way. In some nice way. So in particular, I want to say that given, let's say eta 2, so it's completely symmetric, so I'll just pick one. Given eta 2, so let's say I explored it, like in the Ising model, I could have explored this bit, so now that became A. Somehow log of eta 1, please SME in whatever, P minus A, right? So now this is A. I hope you see what I mean. I want this property because it's a consistency property that comes from these discrete ideas. So I hope you think it's reasonable to require. And the same if I switch 1 and 2. So what I always know how to do for several I have one random object, so I can take several random objects independently. So I could have a product measure of two independent things, which would give a probability measure on the pair, but this is the wrong one. Gauss is not gonna satisfy this, right? But I can start from that. So let's say dp like eta 1. So notation is a little bit not so consistent, but I try to give you idea and then I write a bit better in the note. And here I want this question mark thing. And actually, again, so if I believe that these measures are absolutely continuous, which means that this Radon-Nikodym derivative would exist, which kind of gives the interaction. If I can write it down, then I have my guy. So I need to prove that it satisfies what I wanted. And okay, so this you can do. Maybe I just write explicit because it's really from already there. So I don't want to write it down here because I want to write you this guy that actually satisfies PPC.
So
I need to erase.
what you write as dp eta 1 means the law of eta 1 as if eta 2 was not existing? Or?
Exactly. So the denominator downstairs has independent product measure of eta 1, eta 2. Upstairs is what I want. And what is the Radon-Nikodym derivative is essentially what is here, kind of. But you imagine A is given by that. So instead of A, so here I have, okay. I think eta 1, eta 2, right? And so here comes some, it's a bit tricky to modify this. But instead of this A, I just have it, that's the idea. And maybe this side we don't. It's almost like this. But the point is that if I do that, this upstairs is not necessarily probability measure. This probability measure has total mass 1. If you calculate the total mass of this, is something else, right? So actually, this denominator here miraculously makes sure that the total mass is 1. So somehow, maybe this is a little bit impressionistic, but this derivative, what is it? Interaction, right? In this model, because here is independent, and here is not independent, and here is my thing. And total mass of this non-independent one. This is people call partition function sometimes, right? And if you see what it is, let me call it Z. So it depends on the domain and this. I should probably be able to write it. So there is going to be this kind of independent, I don't know how to call it now. Expected value of all this Radon-Nikodym derivative, which has the indicator that they don't touch. I can fit it. Because otherwise it doesn't make sense, and times the exponential c/2 of this. No? I take these separately because they are not random, right? So here is times, let's say product. I only have 2, but I'm a little bit lazy. I have like xj and yj. And then I have this domain. And here I want Poisson kernel. What is the good? Maybe h is good. And this whole thing is the power h1, 2. So this is the Poisson kernel in the domain with between 2 boundary points. So I can write it down, but maybe for the sake of time, because I don't want to keep you here for the whole lunch. So please ask what you want me to write down. So there's this prefactor, which actually coincides with what you get from here when you do a computation. So I can do it if you want, or I can do it privately. And then there's this guy is just whatever is here. So that would be the total mass of the measure I get. And now what is it? It's a function of the domain, possibly metric, marked points. Yeah. And then I can move these marked points, and there I get the BBC equation. And what I wrote here, you can protest, how do you differentiate this, right? So there's other ways to write this. So it's not trivial to prove that you have BBC equation. And then what happens is that for each configuration of curves, I somehow get one solution to the BBC. I can cook up somehow all of them in this way and really check that there's the BBC. So then hence, it ought to have to do with some field like that, but I don't know how to construct that field. So I'm very happy if someone tells me how to construct it.
So this was a work of Dubeda, this part?
I think this is Greg Lawler's idea originally. It's from this, so this, what's here is the conformal restriction property.
No, but
So Lawler and Werner kind of.
But the BPZ equation?
Right. So Dubeda did something not in this way, but he was doing the local definition where you grow from the points, which I'm omitting because I thought maybe this is too much probability. So this was, so Lawler has some paper, but then there's also me with Howard. Lawler and Kostron, I think. But they don't prove the BBC equation, they just do the construction. So it was the first place where you get the BBC. Maybe it's my paper. So I don't remember if I did it first or someone else. Sorry, I don't care about too much who did what, and I forget. But I was investigating this a lot because I wanted to solve also probabilities of how they connect, because there can be different crossings. So you see this Cardy's formula that I haven't come to yet. But when Cardy was discussing this boundary CFT, and he said, okay, this disorder, boundary condition changing disorder is this thing, then he calculated crossing formula, right? Which is a 4-point function, which is outside of the minimal model, so you can check. And what I get from here is the same. So this is essentially Cardy's formula. So maybe from here it's not obvious. It's the Cardy's formula for a crossing like this. Yeah.
Maybe we should stop.
I'm thinking we should stop, but make wishes what you want next time.
Maybe one quick question.
So in the yellow book, we learned that first that the stress tensor is the response of the log of the partitioning function to a change in metric. And then we learned that if you take 2-point functions of the stress tensor, you can get out the central charge. But now here we are learning something else, which is that somehow you can do some restriction in probability theory, and then you can get the central charge this way.
Yeah.
So is there some kind of explored route to go from one of those statements to the other?
I think it's not, there's no literature about it. You can write this in terms of the Schwarzian derivative, which maybe you can try to relate to the stress tensor.
Yes.
Maybe another way is if you do the semi-classical limit, you kind of only see the geometry. Yeah, I don't have a very good clear answer at the moment for this, because yeah, also this is not the infinitesimal change really. It's a kind of big change. So infinitesimal change that
you could make it infinitesimal.
Yeah, so you could make it like that. And if you do it in the interior, you need to modify this a bit.
Because another thing I remember is that Cardy tried actually to do something to the curve to get out the stress tensor.
Yeah, so there are some kind of correlation functions that were associated to stress tensor, which is when the curve is visiting some points. Yes, there's also a paper by Wendelin and maybe about that. But this is only for the central dot zero case somehow. My knowledge, maybe Cardi had more.
Okay, so why, this seems to only see the conformal way H sub 1, 2 versus if I have a general, Virasoro, I have all sorts of
Yes.
possible other singular vectors. So why this one?
So you see the other ones also, but you need to do fusion. So I don't have the complete description of the CFT yet. Now I just discovered that there's at least that one field somehow. So if you do a fusion of these 2 points together, these together, you get somehow 2 curves from the same point. So this becomes H13. And then you can keep on doing this. You get the first row of the catch table that has to be somehow in your theory by these arguments. And once again, I don't know what the fields are, but the correlation functions. And you get higher order BBC equation also. So then you can have a closed OPE, if you will, once you understand all of those fusions. So you can calculate them from this. Yeah. It's kind of construction of CFT because I don't know what CFT I'm looking at. So I need to figure it out. So I start from what's the basic object and then try to, And you see it's not a minimal model because there's more. And yeah, I guess we are learning in other talks that there's even more complicated CFTs built from these random curves. But okay, so I'm happy to explain more basic or non-basic sometime. Probably I shouldn't keep you from lunch.
Maybe we should go to lunch
Yeah.
and we can ask questions after lunch and tomorrow.
Yeah, thanks.
If you need a lunch ticket,
En quelque sorte, c'est un peu dans la direction
I mean, I followed her,
restriction
but I,
vers
because she said that somehow I
un peu mon dire. Mais en fait, l'idée, c'est si je prends un petit bloc comme ça, un petit A, j'explore un peu l'intérieur de manière.
So you can do this Cartesian reflection to get something in the
C'est un peu équivalent à perturber un tout petit peu la courbe de manière un peu
But can you try both fields, like maybe starting to the point?
So
La
unfortunately,
restriction, ça dit quelque chose sur les
yeah, so
perturbations
after
à
the
dimension.
party trick, I get something that's
I just, I can.
C'est notre papier
like,
avec Guillaume
right, I mean, I just don't understand
qui
how,
s'appelle CFT,
like, what you're
So this
picking
is something
there.
which
Right,
has
so it seems like you have to pick this cap size and then,
or you can have
maybe
more.
just,
Or maybe you
you know,
have
give
like,
that, with
like bulk and
pegging
bulk.
down
And maybe
only the theory that gives you this charge and
Il
this
répond.
conformal way.
La question sur comment aller de
And I guess
So if you want
if
to
you
know
know
Ah,
this charge and you know,
like the
à
bulk,
stress tensor par exemple.
you know, you have some
Mais vous allez au
specific field.
I guess you're
Non, non,
conformal
parce que
way.
stress tensor, on est égard à 0. Donc,
Yeah, so we can
si tu as tous les opérateurs dire à 0, tu te dis que peut-être
Must know this is gonna be zero from how many
de fonction définition.
might already
En
know.
gros, ce que je disais, c'est que
I don't get it.
la manière un peu facile de voir le truc, c'est
And
vraiment
you can try
la
something. That's what makes it feel better.
si tu manges un tout petit morceau de ton domaine, un tout petit morceau du bord de ton domaine,
This doesn't have a
tu
meaning.
réuniformises maintenant
Yeah,
le
it's
truc,
like
hein.
So it's a bit
chicken
harder
and
for
Comme
us
si
to
tu avais en fait gardé ton domaine
What
fixe,
kind
mais tu avais perturbé un tout petit peu d'accord.
yes, you have a construct.